This used to be our Potentiostat output. There are so many texts and data. At this rate, we need to extract our data manually to visualize the measurement results. First, we copy the measurement data from the log. Then we create a new file and clean the data. Add the column name on top and save it to CSV file. After the CSV file is created, we ran Python Notebook and include the file to calculate the result and plot it. Doing this once or twice is doable. But when we have to do this for every measurement, it's cumbersome. Not to mention, we have to give them command and we need to remember the device parameters, which are important. Therefore, we made a web app that can communicate with the device better than this approach. We made the web app for both front-end and back-end. We used Node.js and Express.js for our back-end. The back-end routes our requests and communicate with the microcontroller through serial port, as we used UART protocol. The front end, on the other hand, provides us a dashboard and parameters for our devices. This way, we don't have to remember all of the assigned command number. Just fill the parameters, then submit, and we communicate with our devices. But how do we capture the data? Here's how we visualize the data flow. First, the data flow from the microcontroller to our PC through UART. The data is translated from UART to USB packet in so that it can be recognized as a local serial port. In the backend server, the incoming data is stored as backups and help us to investigate if there's any anomalies in either our devices or the app. The device outputs variation of data, from a notification to measurement data. To make sure that machine can process our important data, we format them as a JSON so that it can be parsed and processed easily. If you look at the serial monitor, it explains a lot why some outputs have JSON format so that it can be processed by our web app. In the backend, the server checks the incoming data whether or not the data can be parsed to JSON. The server would ignore if it doesn't have one, but it would parse the one with the JSON format. The data can be parsed and determine the state of the device. For example, if the state is start, the app would plot the measurement data, or else it would just show the data on the dashboard. At first, the web app codebase is simple and lean. We only used several libraries such as Express for routing, Socket for communication with the front end, and Serial Port for communication with the device. Our routing app is simply displaying the HTML and processing the request from the web page. One of the handlers is handling the request from the web app and translating the HTTP post request data to a string of UART data our device understand. Serial port library is used to communicate with the device, like sending a command or handling the data from the device. Handling serial data usually involves WebSocket. WebSocket is used for communication between server and client back and forth. This way, client can receive as well as send the data. In this case, the front end sends data regarding measurement parameters and setup. Also receive measurement data and state of the device. To plot the data, we use Plotly.js as the graph updates automatically and the graph is interactive. Although this web app has helped us significantly, the codebase is messy and would be hard to maintain in the long run. Therefore, we use AI to help us, making our codebase, having less spaghetti code, more maintainable by making it production-grade codebase. And boy, the code changed a lot, even if the essence doesn't. The coding style is completely different to ours. Contrast to our direct approach of declaring object, the AI has a little bit more complexity, yet it has some modularity. Because of this, we have to observe the changes, learning and understanding the code, and test the code. Fortunately, the AI made a mock serial port that allowed us to perform tests without having to connect the Potentiostat. Despite all that, the AI isn't perfect. Some of our critical logic was removed, so we have to patch it on our own. After understanding the flow and the code and adding more improvements to our codebase, finally, the app is way better and more maintainable. Despite some capabilities are still underway, but it's working though. So this is how we run the web app. First, we run the code. Make sure that you have connected the microcontroller to the PC so that the web app recognizes it. After this, we can go to our local web page. In this case, we use port 3000. Now, we are setting up the parameters for the measurement. We are performing cyclic voltammetry for ferricyanide. Enter the input and click apply, and the command is sent to the microcontroller. It's way easier, right? Now, we do similar things for other parameters. Now we check the voltage in the Potentiostat to make sure it's running. The data shown are still raw data, not the calculated one, because it hasn't ran. The data shown in the dashboard, not plotted. Now we click Start Measurement to start the measurement. The data would be plotted to graph and it would update the scale as we go. During this measurement, we used internal ADC instead of the external one due to some issues. Since we output raw data from microcontroller, we calculate the data first before it's being plotted. We have two plots converted DAC value against current on top and the reference voltage against current for the bottom. Click Save Measurement to save the data. We save the measurement data in the data folder and we can see the data and the parameters are recorded. We can also look at our previous experiments and the results and enter the file name from the data folder and the data would be plotted. So far, that's how we communicate with our Potentiostat devices using a web app. It's not finished yet, but we'll improve it as we go. You can access my web app on GitHub. Thank you so much for watching and see you in the next videos.